Hey everyone, welcome. Today, we're going to pull back the curtain on the AI that we all use every single day. We're not just talking about cool algorithms here. We're talking about ML system design. Think of it as the actual blueprint for how AI thinks, how it learns, and serves us out there in the real world. So, let's just dive right in and see how these incredible systems are actually built.
You know the feeling, right? You open up your favorite streaming app and bam! Right there is the perfect movie you didn't even know you were looking for. Is it some kind of mind reading? Psychic powers? Well, not quite. And that exact moment of magic is our entry point into the world we're going to explore today.
Yeah, that seemingly magical recommendation, it's the result of an incredibly complex, carefully designed system working behind the scenes. And in this explainer, we're going to completely demystify it. We're actually going to build one, step by step, right from the initial idea all the way to a live learning product.
Okay, so our journey, it doesn't start with fancy code or massive data sets. No, it starts with a simple question. See, every great engineering project, especially in machine learning, has to begin by deeply understanding the why long before we ever get to the how.
This right here is step 0. It's the absolute foundation. Before we even think about writing a single line of code, we have to define what success even looks like. Are we trying to get more clicks, increase watch time, and maybe most important of all, what are our constraints? For our recommendation system, if it takes more than a split second to load, you're gone, right? You'll just leave. So a hard constraint like latency must be under 100 milliseconds ends up dictating every single decision we make from this point forward.
So, with our goal defined, it's time to move to the raw materials of machine learning, data. But, raw data isn't really enough. We have to shape it, mold it into these intelligent signals called features. These features are the actual building blocks our model is going to use to make its predictions.
Now this is where things get really interesting, because what this slide shows is that there are basically two parallel universes for features. Offline, when we're training the model, we can afford to be slow. We can be expensive. We can analyze a user's entire 2-year purchase history if we want. But online, when that user is sitting there waiting for a recommendation, we've got less than 100 milliseconds. We can only look at super recent stuff, like what they've clicked in the last 5 minutes. These two worlds, they have completely different rules.
And this is where so many ML systems fall apart in the real world. If the way you calculate a feature, say number of recent clicks, is even slightly different between your slow offline training world and your super fast online serving world, your model's predictions are going to be completely garbage. This problem is called training serving skew, and it is a silent killer of model performance.
So how do we fix this huge problem? Well, the answer is a really brilliant piece of engineering called a feature store. Think of it like a central library for all of your features. You define the logic for a feature just once, and the store guarantees that the exact same calculation is used for both historical training data and for live real-time requests. It becomes the single source of truth that bridges those two different worlds and just totally eliminates that dangerous skew.
All right, we have our goals, we have our features locked down. Now, it's time for the training montage. Cue the 80s music. This is where we take literally billions of data points and teach our model to see patterns. But doing this at web scale, that's a massive distributed systems challenge.
Let's be real. You can't train on billions of examples with just one computer. So you've got two main strategies. The first is data parallelism. That's where you chop up your data into chunks, give a different chunk to many different machines, and they all work on training the same model together. But what happens if the model itself, like GPT-3, is just too enormous to fit on one machine? Well, that's when you need model parallelism, where you literally split the model across different machines.
And to get even more efficient, we can use a really clever combination called pipeline parallelism. The best way to think about this is like an assembly line for our model. You split the model into stages, put each stage on a different machine, and as soon as one machine finishes its part of the job, it passes the work to the next machine in line and immediately grabs a new piece of data to work on. It's all about keeping every part of the system busy, all the time. No wasted cycles.
Okay, our model is trained. It's smart, it's powerful. But right now, it's still just sitting in the lab. Now we have to release it into the wild, into the production environment, where it's going to face millions of real users and has to perform flawlessly. This is where the real test begins.
And right away, we face a fundamental choice. We can go with badge serving, where we basically pre-calculate everyone's recommendations overnight and just serve up those static lists the next day. It's simple, it's high throughput, but the results can get stale really fast. Or we can use real-time serving, which generates a brand new prediction the instant a user makes a request. This is amazing for freshness, like for live fraud detection, but it's way more complex and puts incredible pressure on that latency budget we talked about.
And this is such a critical, non-obvious point. We might spend months building a new model that's, say, 2% more accurate, but if it adds 40 milliseconds of latency to the user's request, it could actually hurt the business more than it helps. In the real world, you have to remember, speed is a feature. Sometimes a slightly dumber model that responds instantly is way more valuable than a smarter one that makes the user wait.
So, our model is live. It's serving predictions to the world. We're done, right? Party time? Absolutely not. Deploying a model isn't the finish line. It's just the beginning of a never-ending battle to keep it performing well as the world constantly changes around it.
You see, over time, all models degrade. This is a phenomenon called drift. There's data drift, which is when user behavior simply changes. Think about summer shopping habits versus winter shopping habits. But then there's concept drift, which is way more subtle. This is when the meaning of the behavior changes. What signaled a likely purchase last year might not mean the same thing today. And if you're not constantly monitoring for these silent killers, your model's performance will just slowly die.
So let's say we've built a new model and we think it's better. All our offline tests look great. How do we know for sure? We can't just trust those offline metrics. The only way to get the ground truth is with a live A/B test. We serve the new model to a small percentage of users and the old one to everybody else. Then, we measure what really matters. Do they actually click more? Do they buy more? This is the ultimate test of real-world impact.
And this brings us to the final and maybe the most important piece of the entire puzzle, the feedback loop. Every single prediction our system makes, every click, every purchase, every time a recommendation is ignored, that's all new data. We have to build systems that collect this data, learn from it, and then use it to automatically retrain and improve the model. This is what turns a static model into a living, learning system that actually gets smarter over time.
So there you have it. We've gone from a simple business question all the way to a complex, scalable, and continuously improving intelligence system. You see, building the brain of an AI isn't a one-time thing. It's a constant cycle of designing, deploying, monitoring, and learning. A system that can learn is an incredibly powerful tool. The only question left, really, is what problems we want it to solve, and what we're going to choose to teach it next.